I'm Peter Gleick. I'm the president and co-founder of the Pacific Institute in Oakland, which is an independent research and policy group working on water issues, environmental challenges, impacts on local communities, and sustainability. A lot of work on water and climate, water and energy. And I'm talking here at this AGU on hard water problems, difficult water problems, both existing and emerging, how to think about them, how to categorize them, and hopefully a little bit about how to address them.
Water is an issue that a lot of people haven't quite connected with the climate issue yet, but we go forward assuming that the water resource that we've had for the last 200 years will always be available to us. But in a climate change regime, that's increasingly not so. What can you tell us about that?
Yeah, that's right. I'm a hydroclimatologist by training, so I've thought about water and climate issues together for a long time. But people often think about them as separate, which is a little ironic. The hydrologic cycle that we all learn about, the evaporation, formation of clouds, condensation, rainfall, runoff, evaporation again. The hydrologic cycle is the climate cycle. And as we change the climate, we will inevitably, and I would argue are already, going to affect both water availability and the systems that we build to deal with water. The infrastructure, the water treatment plants, the reservoirs and aqueducts, the hard concrete that we've put in place to try and address water availability challenges. Inevitably, those things are going to be interlinked and interconnected and affected at the same time.
I think a lot of people on the climate denial side seem to think that we can continue to build large thermal power plants, coal, gas, etc., and continue these water-intensive processes of mining and fracking, especially in arid areas like the American West and Asia, without coming up against any barrier in terms of water limits.
So there are lots of disconnects in the water, climate, energy area. One is we simply don't think about water and climate together, which is a mistake. Another is we assume that the past is prologue, that the future is going to look like the past, that the systems we built and operated in the water area under the past climate are going to serve us equally well under future climate. And the models tell us, and reality is beginning to tell us, that that just isn't the case, that we can no longer assume, in the parlance, stationarity, that the climate's not going to be changing, that our extreme event frequency and intensity isn't going to be changing, that the water available for agriculture or for power plants or for municipal use in the past is going to be the same as the water that's available in the future. It just isn't in most places, and we're not good at thinking about how to plan for those kinds of changes, or how to redesign our systems, or how to think about different energy futures that are less water intensive. But if we don't, we're going to run into problems. And in fact, we already see examples where we're running into problems of limited water availability, a need to change our energy systems or the way they operate. Or in recent droughts, a good example is we've had to shut down or derate power plants because A, water wasn't available, or B, the thermal limits on streams were being exceeded. It was getting too hot for fish. And that's a good example of the connection between energy and water that we need to start thinking about.
So a lot of people don't realize that, correct me if I'm wrong, something like 50% of the surface water withdrawals in the United States go to power generation. Is that correct?
So it's under 50%, but it's close to half of all of the water withdrawn in the United States goes for power plant cooling. Now, there is a distinction between withdrawal of water and consumptive use of water. A lot of that water goes out of the river, goes to power plant cooling, goes back in the river a few minutes later hotter, and that runs up against temperature limits. That's the example we've seen where power plants have had to be derated or shut down during droughts. But it's not necessarily a consumptive use. But the other associated problem is that there are parts of the United States where there isn't even enough water for new withdrawals for new power plants, even if it's not a consumptive use. And the southwestern United States is a great example. The Colorado River is a great example. We use all of the water in the Colorado River. Every drop, it's withdrawn, it's used, it's put back in the river, or it's withdrawn and it's put on crops and it evaporates and it's gone. No flow reaches the mouth of the Colorado in an average year anymore, which ironically enough is in Mexico, not in the United States, because we use it all. So we might want to build more power plants. We might look to a river like the Colorado for more water to cool those power plants, but increasingly that water is just not going to be available, and we're going to have to either use different kinds of cooling systems or look to non-thermal power plants, not nuclear, not fossil fuels, but some of the solar, some of the wind, some of the renewables that typically require a lot less water per unit energy.